Thanks for coming out, and thanks for everybody's watching and attending. My name is Daniel. I currently work as a postdoc in upstate New York at the AFRL, that's the Air Force Research Lab. And we have a pretty good developing quantum team up there. We've got a little bit of everything going on. We've got some people developing for photonics, recently some people hired on board to start building our first superconducting qubits, and for about 3-4 years now, some trapped ions. So Air Force has a little bit of everything, and we just want to stay in the game because we know this technology is going to be around for a good while. So that's my background, and today I'll be showing you sort of the basics of Qiskit, sort of just to get your feet wet, show you what it means to run a circuit, and then we're going to implement it doing a Grover's Oracle demonstration, and that'll be sort of my talk. I originally had thought I was going to go earlier in the day, so I apologize for any repeated information. But it never hurts to hear the same thing a couple more times. So differences between classical and quantum coding, as we've already talked about. Bits versus qubits. Your bits live in this 0 and 1 space. Your qubits live in a completely different space. And that's really fun. It opens up the new ball game. And so it comes with its own set of challenges, and you have to change the way you fundamentally think, as we've seen already in some of these great presentations. I can't top some of those awesome visuals. But for instance, when teaching CS to a student, right, and OR are very intuitive gates, because we think of that, it's almost wired into our brain the way we go day to day. But then you have to remove those when you start quantum coding, and that takes a completely different mindset. Instead, and it takes a while, is you need to start thinking about what your quantum code is doing in this sort of qubit space. And I liked the emphasis earlier when somebody said, that I can easily imagine students getting hung up on bits, right? So when you read a classical code, you think of bit by bit, line by line, gate by gate. But when it comes to quantum, you need to think about the superposition state. The bits are there and the gates are there, but their impacts are felt in a completely different realm, as shown here by a Bloch sphere in sort of 2 rotations. So that takes a little bit of training, but it's not so bad. Here's just a very quick example of some quantum gates we've already seen. X being the analog to a NOT gate. So we do have that. And then the Hadamard, which is sort of the first really quantum gate in my opinion, because now you create this superposition state. And we're going to see quite a bit of that. And then as you develop and you get more experienced, your gate circuits start to become more complex to the point where unless you are almost like a savant and you can visualize this 2 to the n space, you see a circuit like this, and this happens to be QAOA, which is a more advanced algorithm I wouldn't give to a student right off the bat. But you look at these and you start to sort of dissect it piece by piece, and it becomes very, very difficult to traverse along the way of, okay, what's my quantum state after, say, the second round of ZZ gates, or these, interconnected, entangled C-naughts. It all gets very sort of messy. And so Python, and particularly Qiskit, what I'm going to talk about today, is a great tool to sort of help you visualize it along the way. It's just the first language I gravitated towards, but I have experience in all of them. And really, it's the visual clarity that I think is most important when you're looking at quantum states and you want to see, for instance, with the circle states we just saw, I want to apply a gate, and I need an immediate sort of visual response so that I can train my brain of how to think and develop. But like we've already stated, there are a lot of challenges currently with quantum coding, both mostly in hardware, but then in also algorithm design, which is my personal background and where I do my research. And that is, when it comes to the physical computers, they're noisy, fidelities, coherence times, those are all issues that will get solved going forward. And then as those issues start to reveal themselves and get solved, it opens up more avenues for algorithm design to say, okay, well, say 5 years ago, I couldn't expect this many qubits, so I just steered clear of implementing an algorithm down path A. 5 years later, 10 years later, now my qubits are much better, and I can return back to some of those routes. Okay, so let's jump into Qiskit. This is IBM's platform for quantum coding. It's Python-based, which is really nice. So anybody who knows Python can just jump right in. Syncs with all the libraries that you already know well and good. It comes with both a simulator, which is what I'll be showing you today, and that's what I would recommend anybody to start on, because getting onto a real quantum computer is A, expensive, B, it's noisy and it doesn't work that well, so unless you have something very targeted in mind, like say you want to benchmark something, I think working on simulators is probably the way to go for several years down the road, just to demonstrate. And they even have noise simulators, so you don't need the real quantum computer to get noise into your algorithm. So here's a snapshot of some code written in Python mixed with Qiskit. And the things I want to highlight, and we're going to dissect this, don't worry. But as I mentioned, because it's Python-based, you can just jump straight in and start defining your own functions, which is sort of how I got started. Python, was my first language, and then when I went to Qiskit, I started using all of their default functions because I just thought, that made the most sense. But after a while, I realized, maybe not everything Qiskit has out the box is visually clear or even streamlined enough. So you can define your own functions. And for instance, down here, the output that you see from this Python code is not something that comes out the box with Qiskit. I have sort of print statements down here to show, that's my quantum state at the very end, but I by hand wrote a function. You can see it in the middle of this code. It's called oq.wavefunction. And I wrote that because every single time I wanted to see my answer for my state function, I got so tired of looking at the default vector that had complex numbers, and I couldn't tell what quantum state was in what space in a vector, so I took, a couple days and I wrote this function just so that I could see it clearly, and it's helped quite a bit. All right. So on the screen here, this is a sort of very simple circuit that we're going to start off by building in Qiskit. We're going to do it with 2 qubits. And to the physicist, you read this and it's a very straightforward quantum circuit. 2 qubits, Hadamard on the first qubit, X naught on the second qubit, and then that weird half circle symbol is a measurement. When you're dealing with simulators and you're trying to teach a student or whoever about the impact of a quantum algorithm, the measurement at the end, sometimes you don't necessarily want that, but it always is important to keep in mind that on a real quantum computer, you need a measurement at the end of the day. So in this example, we have it, but the real merit of going through an algorithm is usually in the state function and the wave function and the way the amplitudes and phases all blend together. So 90% of what you're interested in is that, and then the measurement at the end is sort of like the caveat, okay, I did this and I built this cool wave function, but will the measurement kind of screw things up for me, or what can I expect? Okay, so let's start building this. Just like any good old Python code, we start with step 0 is our imports. For this particular example we're about to run through, the things from Qiskit that we need are a classical register, quantum register, and a quantum circuit. Those are your 3 sort of building blocks, your Legos, if you will, for Qiskit code. Here on this slide, I just have a couple things that you also need, like AIR, which is one of the, I believe, 4 different packages that Qiskit offers. AIR is the one that I would use almost on a daily basis because it comes with the simulator. Execute is just a function that's going to essentially take everything you put into your quantum circuit and run it. And then because we know at the end of our code we need measurements, we need a measurement simulator. Obviously, it's not a quantum simulator, so it's just going to go back to being a classical, however you do random numbers in classical Python, same thing here. So once you have all your imports, step 1 is sort of creating the laboratory, if you will. To do that, as I mentioned, the 3 building blocks are a quantum register, classical register, and a quantum circuit. So to sort of quickly go through what each one does, your quantum register holds your qubits. not surprisingly. Classical register then is going to hold classical qubits. Those are just ones and zeros, nothing special. And then your quantum circuit is sort of the object that holds it all. So what we're going to be doing is essentially amending the quantum circuit, this what I'm calling QC in my code here. And as you can see, even the first input inside the parentheses to my quantum circuit is my classical register and my quantum register. So I first define those two objects, and then I put them in my quantum circuit. But now it's sort of just like an empty book that has no instructions, no measurements, no nothing, but I've created all the right placeholders for where qubits instead. Okay. Adding gates. Very, very straightforward. The syntax, I think, is as simple as it needs to be, gets the point across. So up in the top right corner, a little bit cut off, but you can see just as the picture shows sort of going from left to right, qubit 1 gets a Hadamard gate and qubit 2 gets an X gate. Those two get directly written into Qiskit in the following lines of code. QC.H, QC.X. And then if you go online and you're interested in all the different gates that Qiskit has, there's a long, long list. And those include all your poly gates, your control gates, your phase gates, etc. And if you get a little bit more advanced, you can define your own gates. So just, if you know there's something you're going to use over and over, you can define it and then call it yourself. As long as it's constructed from the basic ingredients that Qiskit gives you, Qiskit has a lot of flexibility in that regard. So now, as you can see, these three things are being appended to QC. And from the previous slide, QC was my quantum circuit. So now I've got an object that has qubits. It knows where those qubits are. It knows where those classical bits are. And now it knows what to do. However, it hasn't run it yet. In order to do that, we need to execute. And there's a couple, more things you tack on. The inside the parentheses is what I want to highlight here. The function execute, you pass it the quantum circuit object. That's the visual representation, what I have up there. Then you pass it the simulator that you want it to run on. That could be a simulator with or without a measurement. And then shots. Now shots is essentially how many times you're going to run this thing. Why that matters is because for measurements, every time you make a measurement, you collapse your wave function. And sometimes you need to do many, many measurements or many, many trials in order to build up your statistics. That's how, when you work with a real quantum computer, you have to think at the end of the day, if it's not something like Grover's, which is an amplitude amplification, where you're going to get it in one shot, oftentimes a lot of algorithms need repeat trials. Say on the order of 10,000, if that's a good enough number to build up this landscape of probability. And then there's just a couple more things like get the results, show me the results, etc. And then the print is just a nice dictionary. And in this particular example, we ran it one time and the state we got was 1, 1. If we ran it again, we could have gotten a different state. And so this is sort of, if you will, this is as close to getting on a real quantum computer as you need, in my opinion, because you're running the circuit, you're getting your measurement results, and there's nothing in between. You didn't cheat, you didn't look at the wave function, etc. So now we go back to our circuit and we ask, what was the expected result? Sometimes it's fun in quantum coding. I do it from time to time. I just throw gates in there and I see what pops out because that's sometimes how you discover new things. But at the end of the day, obviously, it's not a good strategy. So if we revisit the circuit that we just constructed, it was a Hadamard on the first, an X gate on the second, and I have the math down here to show what the wave function was at the end of the day. And as we can see, it's just a 50-50 state represented by that 1 over root 2. And so I was either going to measure the 0, 1 state or the 1, 1 state, and it just so happened when I ran it and printed it, I got 1, 1. A nice thing is if you upped the shots to say 100, you're definitely going to see both results, and you're going to then get a dictionary that says 45 times you got 0, 1, 55 times you got 1, 1, And then that matches your intuition. You see, okay, well, that was the wave function, and it's nice to see the measurements in agreement. And again, here's just the same state. So what can we say about it? It's nothing too special. It's a 50-50 state. Yeah. And here it is, the full quantum code for creating that state, running it, measuring it, and viewing the results, all done through Qiskit. I like to, and when I write my code, I like to sort of bracket things off by where they sort of exist to me mentally. Like, for instance, at the top 3 lines of code, that's just sort of my table setting, you know, putting out all my plates and dishes, all my registers, defining them and storing them where they need to be. Then the middle block of code, that's my quantum circuit. Now, that's where you spend most of your time thinking about the wave function. That's where sort of, if you go back and things weren't right, your measurements didn't agree, that's usually where you go back and amend your code. And then at the very bottom, once everything has been taken care of, it's sort of just like, okay, run it, show me my results, give me the dictionary. And as you can see, like I mentioned, I upped the shots here to 1,000, and it was still always a 50-50 state, and in this particular time, I got pretty close, 493 and 507 between the 2 states I had created. So this is good. This is a nice simple code. It sort of gets your feet wet, and you can sort of see how, if you wanted to build more advanced circuits, where to go. Now, that was for measurement-based, which I had already mentioned is not my favorite because it misses out on a large portion of what quantum coding is all about and algorithm design as a whole. The measurement at the end of the day is sort of the bane of my existence because it bottlenecks what you spend so much time creating in these wave functions. So what if I don't want to do that? What if I want to actually look at my wave function because I'm not sure, sort of I'm intermittently creating this algorithm and I need to sort of get more hands-on? In Qiskit, if we want to do that, we switch our simulator. So if you jump to the bottom of this line of code, instead of m_simulator, which is what I would use for a measurement, I use s for state function. And then at the bottom of I just print this wave function after executing it, and there it is. Now, that print statement at the bottom shows you that you have sort of this 50-50 state. 1 over root 2 is approximately 0.707, so there they are. And as we had already seen, it exists on 2 out of my 4 possible states of this 2-qubit Hilbert space. But the issue here is it's not visually clear. If I gave you that bottom vector and you didn't know what Qiskit was, or you didn't have, if someone hadn't told you, those 2 placeholders in that vector could be any of the 4 states, right? Could be 0, 0, 0, 1, 1, 0, 1, 1. So that was an issue that I found because I was working through these algorithms, working through Qiskit, and constantly coming up with these long, tedious vectors that were holding states like this. And I spent more time looking at those than I did actually trying to understand. So that's why I created, that function earlier that's going to make things pretty for us, and we're going to see more examples of that through this demonstration. Okay. So that was the basics of Qiskit. Now, the fun part is I want to show you sort of how you would use Qiskit in sort of like a teaching sense. We've already talked about Grover's and how it's an amplitude amplification class algorithm. The full Grover's requires mostly, 2 phases, an oracle and a diffusion. And it's the oracle part that's really the challenge of Grover's, both from a conceptual standpoint. The first time you learn it, that's sort of the mental hurdle. And then on the other side of the coin, when you go to modern research and modern efforts of quantum algorithm, implementing oracles is still a huge open question for algorithm design. It's not a tedious thing because once you start to see how much work goes into creating this oracle, it almost defeats the purpose. I won't say that, put an asterisk on that, but it almost defeats the purpose because you'll start to see just how many qubits you need, how many gates you need. And then when you turn around and ask, okay, what was my speed up, it can be a little bit discouraging. that's why I say it's still an open question, because there's multiple ways to implement an oracle, and I'm going to show you just a very basic one that would not win out against a classical computer. It would be something more to give to a student who just needed to sort of understand the concept of what an oracle does. And as you can see in this picture, so the bars in this picture represent your amplitudes, probabilities. And so at the end of Grover's, you had a state that you wanted to find. Say, I love the phone book example. You have a phone number, but you don't have a name. So if you go to a phone book with a phone number, you're sort of out of luck, and you're just stuck going through the thing case by case. What Grover's will do is it'll use that phone number to boost the amplitude of finding that particular person after a set number of iterations. And the algorithm itself is promised to be quadratic when you write it down mathematically. That quadratic speedup, though, there's an asterisk on that because it compares steps classical and quantum, and that's not always a trivial thing. Classical computers are just so fast that it's really hard to say exactly what is one quantum step versus one classical step. And so I won't get into that, but this is all we need to get started. So we're just going to work through the Grover oracle component, which I'll explain in a second. The gates that we need are X, H, C naught, and CC naught, also known as Toffoli. We're going to do it with a 4-qubit quantum system, and then the particular state that we want is 0101. So what do we want to get out of the end of the day? Grover's oracle, so just the oracle component, essentially flips the phase on this particular one state. So here would be my starting code, creating my phone book, if you will. I apply Hadamards to my 4 qubits, as shown by the for loop in this code. Again, Qiskit syncs really nicely with Python, so using for loops, easy stuff. And then now look at the bottom. I'm using, again, my custom function that I wrote, oq.wave function. And now it should be a lot visually more clear of what my state function looks like. It's not a hot mess of a matrix or a vector that just has entries upon entries of complex numbers sitting in random places corresponding to states that you don't know what they are. Now, there's all the states as you would give it to, say, a physicist or a mathematician. The 001, the 101 state, etc. So getting started, my equal superposition state, which is the basis, everybody's equal. The amplitudes associated is 0.25. If you square that, that's the probability on each state, which is 1 over 16. So from here, my targeted goal is to flip the phase on one state, 0101. So this would be, a homework exercise, a final, a midterm, whatever you will. That's the goal. And that's that's a very tangible goal to give to somebody, and it's not immediately obvious how you would do it in quantum. In classical it is. You just go into the matrix, find it, flip it, and you're done. But as we'll see, quantum is a little bit more hands-on. So the way we're going to implement the oracle here is through the use of an ancilla qubit. And the basic idea is that this ancilla qubit is going to exist in parallel with our main quantum system. Up at the top here, I'm defining the state minus, which is just the result of applying a Hadamard to a qubit already in the excited 1 state. And the interesting thing is, look what happens then when you apply what happens when you apply a C naught on 1 qubit that is now tied to the minus state. So just very quickly, at the bottom here, I create my initial state of the plus state and the minus state, shown as it is. The plus state is the Hadamard on the 0. Now, the 2 qubits are not entangled, but they are a part of the same quantum system together, hence that tensor product, the circle with the x. So these 2 qubits live right next to each other, and once you start entangling them with C naughts, interesting stuff starts to happen. So in the middle line here, I apply a C0, which is a 2-qubit gate, using the plus state as my control and the minus state as my target. So the result of that is shown in the middle. I skipped some of the math here. But at the very bottom line, the thing to point out is look that our target qubit, the minus state, has not changed. Now that's not what we're used to when we were talking about C0s earlier. When you think of control NOT gates, you think, okay, qubit A is my control and qubit B is my target. Normally, the control qubit doesn't change, and it's the target qubit that's going to receive the effect. But, thanks to the wonderful math of quantum mechanics here, by applying the C0 in this particular combination, the minus sign essentially gets absorbed out of this ancilla qubit, and it interferes and creates a new state on my first qubit. So when I had originally started with plus tensored with a minus, if you rewrite it now at the bottom, I now have a minus tensored with a minus. Okay. So that was a lot of sort of math, all to say that by putting an extra ancilla qubit off to the side, and then we're going to hit it with control knots, we're essentially going to steal a phase from it. And that phase is going to be extracted, brought over to our main quantum system, which is where our phone book Hilbert space lives. And the goal is to make that negative sign appear on just the one state that we're searching for. And so here it is sort of restated. On this top box here, I'm showing you what happened to my first qubit. It originally started in the plus state, 0 plus 1, but because of that C0 interaction, it now transformed into a completely different state, even though it was the control qubit. Now we need to take that idea and apply it and sort of scale it up to our now 4-qubit system. However, we want it to only target one state, as shown by the bottom here. Our goal is this 0101 state. That's the one that's going to pick up the minus sign, and nobody else in our system. If anybody else picks up a minus sign, then our Grover algorithm essentially won't work. So how would we do that? Well, to skip back here, we started with the plus state in our first qubit. So what is the the 4-qubit equivalent to the plus state? 4 Hadamard's, 4 plus states. So the idea here, if you were to write it sort of very, very naively, is shown here in this circuit. Put my 4 main qubits in an equal superposition, create my ancilla qubit at the bottom in that special minus state, which is created from first an X gate to excite it up to the 1 state, followed by a Hadamard to put it in the minus state, and then do this massive 4-qubit control NOT operation. And that would be it. If you wrote this down mathematically, it's totally fine. It'll give you essentially what you're after, not our particular example. But there's a major, major issue with the diagram shown on this, and that issue has to do with what Qiskit can and can't do, and it really comes down to what quantum computing technology can and can't do. And that's the bottleneck of your Legos, if you will. You don't have a 5-qubit gate that comes with Qiskit yet, fingers crossed. So instead, we have to build one. And so the question is, how are we going to build this 4-qubit control NOT gate? To do that, you have to bring in extra ancilla qubits. And this is a concept that takes a little while to get used to, and it can also be very frustrating when you're in algorithm design, because you want to limit the number of qubits for technological reasons. More qubits, more noise, more problems. But then, as you start to realize, okay, well, some of these operations are too complex and I don't have the gates, so I'll just bring in extra ancillas. Now my Hilbert space is just growing exponentially, and sort of that can be a big problem. So here's one basic implementation. So if I want to create a 4-qubit control NOT gate, I just break it up. And I let ancilla qubits hold sort of intermediately some stored values, if you will. And then I recombine them and fold them back in on themselves. And ultimately, it's ancilla 3 at the bottom that's going to receive the net effect. So All right, I just want to make sure. Okay, so ancillas 1 and 2 here in this diagram, they are brought into this algorithm now purely to serve a purpose that has nothing to do with Grover's, but just to hold sort of the values as I go along. So as you can see, the first CC knot, which is a tool that we have in Qiskit, Q1 and Q2, they're going to store information on ancilla 1, while qubits 3 and 4 are going to store information on ancilla 2. And then in the final step, now that I've sort of condensed my 4 qubits down to 2, I do the same process one more time. I condense it down from 2 to 1, and that's shown by the final 2-qubit gate from ancilla 1, 2 with the target 3. So this is sort of the unfortunate reality of when it comes to constructing these things. They get a little bit messy and costly pretty quickly. And when it comes to these higher order C knots, the general rule of thumb is that you're sort of always dividing by 2 each time, because 2, the Toffoli gate is the maximum you've got. So if you want to condense things down from, say, 8, you need to go from 8 qubits down to 4 ancillas, but then those 4 ancillas need to condense down to 2 more ancillas, down to 1 more ancilla, so you've now brought in 7 ancillas for an 8-qubit gate. Unfortunate, but when the technology gets better, we won't even think twice. It's just sort of a consequence of where we are currently in technology, where it hurts me inside to have to code this up. But I'm hoping in 10 years from now, just, a student wouldn't think twice. So here it is. Here is our 4-qubit NOT gate in its full glory. And as you can see, it's longer than what I just showed you for a very good reason. It's one thing to condense the information and to essentially apply that CC NOT, or in this case 4 Cs, onto my target ancilla, but then you have to consider what was left behind. Those 2 extra ancilla qubits, A1 and A2, they don't just get to sort of start over. You can't reset them mid-algorithm. They're now part of the family. They're now part of the problem, if you will. And so in order to return them back to the 0 state, because we're going to be using them over and over and over, we have to undo those operations. So in the first 2 lines, I'm condensing my information of my 4-qubit space down to ancillas A1 and A2, all for the purpose of a final target on A3. And then I have to do some housekeeping, and I undo it, and I essentially reverse the circuit. So this is it in its full glory. And so if you were writing this in Qiskit code, you could say, take this little circuit, call it something like 4C NOT, or whatever you want to, define it one time, write it up, create a function, and then Qiskit will store it for you, and you can call on it over and over and over. And so that's how we would do things in classical coding, because we're just so used to streamlining a problem. In classical coding, when there's something that gets done literally more than once, you write a function so that you never have to write it more than once. And that's sort of the same mentality that we can bring to quantum computing once we're more comfortable with how we want to implement certain things. Okay. So here it is. Here is that 4-qubit NOT that we just talked about. And now we're not doing it for the oracle sense. We just want to see that it worked. And so if it's a true 4-qubit NOT gate, it will only work on a particular state out of my 16 possible. And that particular state is when all 4 control qubits are in the 1 state. Any other combination where a single qubit lives in the 0 state, my 4-qubit CC NOT better not apply an X gate. And we can see that. Down here in the final answer, there's my 16 states, and I've sort of, again, using my custom wave function, it's visually easier for me to break it up into 4 qubits and then my target ancilla. So that's the bracket notation going down at the bottom. The first 4 numbers represent my main qubit system, and then the second bracketed number is my extra ancilla. And if you can see down here, in OQ wave functions, there's actually a middle part that I'm hiding because I don't care about it. Again, this is for teaching purposes, and this is for visual clarity as you're just trying to go through the algorithm. Those two middle ancilla qubits that we just spent all that time talking about, they're extra. They're not a part of my true algorithm, even though they're there and necessary. But if I don't want to look at them, I don't have to. So as you can see in this bottom part, I've written my system. I've asked it to break it up into 4 qubits, 2 qubits, and finally 1 qubit. And then in the next line, or the next entry, show systems, I've got true, false, true. That's just sort of the way I've set it up, such that that middle one I've set to false. Don't print it. Don't show me those extra ancilla qubits because I know they're there. But if I did everything correctly, which was the whole point of those sort of extra C naughts at the end, the housekeeping to reset my ancilla qubits, if I did that correctly, then I can actually truly ignore those ancilla qubits. They got used up, but then I reset them, and I don't have to worry about them. So here's the code. Again, from top to bottom, place setting at the top, define my registers. Here I've chosen to define 2 quantum registers, which is something you can do. Q, which is going to be my main register, and then A, which is going to hold all my ancillas. Q and A are both going into my overarching quantum circuit object. And this is just a total choice. I could have defined 1 quantum register and just put 7 qubits into it, or broke it into 2. That's just sort of, coding convenience, if you will. However you visually see it, Qiskit has some flexibility there. Then the next section, initialize it with 4 Hadamards. And then in the next bracketed off section, there's all my CC knots. That long chain of Toffoli gates, there they are. Each one is sort of saying, okay, first qubit is control, second qubit is control, third qubit is target, and you just have to specify where each one lives. For instance, the very first one, Q0, Q1, A0, that is equivalent to the first CC knot in this diagram, which says qubit 1 control, qubit 2 control, and targeted on the ancilla 1, and so forth. So there's a little bit of syntax you get used to, and then at the end of the day you build it up, and our final answer is exactly what we wanted. All of the states in our system have a 0 state for the ancilla qubit except for 1, which we can see is the 111 state. So we've succeeded. We've written our code. It works. Now the only difference between this and the oracle is that now instead of just having that extra ancilla qubit sit in the 0 state, we're going to use that trick we just talked about, which was to put it in the minus state. So that's the final ingredient. The big hurdle is that higher level C naught. And now we're going to essentially implement the oracle by changing our ancilla qubit not in the 0 state, but putting it in the minus state. I will say, the other difference between this code and what we want is that the 111 state is not the state that we were looking for, right? Our phone book request was to find the state 0101. So that requires one extra ingredient, and that is to sort of essentially trick the quantum system into thinking that that is the state that gets controlled. Or a better way is to say we're going to transform. So we know that our control operation is only going to work for the 111 state. That's quantum mechanical. We can't change that. But what we can do is essentially transform between that state and the 0101 state. So in order to do that, we just apply some extra X gates. So without these X gates, our quantum circuit worked for all ones. But when we apply these X gates, what we're essentially doing is we're picking out the quantum state where we want zeros to be. So everywhere that I've put an X gate just prior and just afterwards is essentially saying, okay, transform between 0 and 1 at that particular qubit. And as you can see, I've got the X gates sitting here on the first and third. So that would mean I want my oracle to correspond to the state 0, 1, 0, 1, zeros being on the first and third qubit, which is our goal. And sure enough, here's that exact code written in Qiskit. Everything is the same, except I've now added these 2 extra X gates before and afterwards. And if I look at my final answer, there it is. The 0101 state, which is the state I care about, now effectively was my control. It, if you will, it's sort of funny to think that like you're tricking the quantum system or transforming it, but that's how it feels like. But at the end of the day, we got the result we wanted, which was that the 0101 state picked up the now 1 state on my ancilla. And since we've got that final component, now we're ready to implement the full oracle. Again, here it is one more time. All we essentially did was transform between these 2 states, the 111 and then my 011. So now when I put in for the extra bit, which is to put that ancilla qubit in the minus state, such that this higher order control operation is now going to steal a minus sign away from the ancilla and store it onto the state that I care about, we have our full code and we have our final answer. This is our Grover oracle implemented in its entirety. And as you can see at the bottom, the 0101 state has a negative phase. So if this were a classical code, this would have taken a freshman 5 minutes or less if they knew how to code in a vector. Not so for a Grover's oracle. It's not a trivial thing to say, here's your state function, and all I want you to do is to flip the phase on 1 state. But as we've already talked about, the issue here is that 1 state exists in a 16-dimensional space, not my 4-qubit space. And so we had to go on this long adventure just to learn how to flip phases, steal phases from ancillas, implement higher order C-naughts, and etc. And I think it's super fun. My background was physics all the way. I knew I loved quantum, but when going through my undergrad and grad school, quantum physics was more of like a subdiscipline, and seeing the opportunities now where you get to learn this in a classroom from an undergraduate level, I'm quite jealous. I would have loved this back in the day, which is part of the motivation of why I created a tutorial series, because I wanted to help students and anybody interested in learning. So thanks for listening. Boom, there it is, our special answer. We nailed it. And this is, again, not even the full Grover's algorithm. There's more components to it. You take this state, and this is just the oracle. You then have to do a diffusion, and then you have to do many iterations, and then you have to make a final measurement. So the story doesn't quite end here. But in a greater context, you can extract the oracle, and you can apply it to different algorithms, and I think that's more important. From my own, personal 2 cents is that, will we ever see a day when we're using Grover's algorithm to look up things in phone books or like implement it on a Google search? I actually don't know. But we're already really close, and I've seen, just amplitude amplification being used across the board in so many interesting ideas. And same thing with this oracle. There's a handful of algorithms that just need oracles. So when you break apart, like Shor's, for instance, is really like 5 algorithms. And I remember I read somewhere, somebody asked him, like, how did you think of this? Because when you go through Shor's from start to finish, it almost seems too much for one person to think about. And Shor's response was like, well, all the pieces were there. All I did was put them together. And I thought, like, darn, that guy's lucky. I wish I could just put 5 pieces together and get an algorithm named after me. But it is those 5 pieces then that is really fun and interesting, because you sort of go through all these algorithms like VQE, QAOA, Grover's, Shor's. You break them down, and then it's totally valid to just say, what happens when I start slamming different parts of different algorithms together? One of which, I'll give an example, is quantum counting, which is phase estimation But instead of using, the matrix essentially that you're trying to estimate a phase on, you literally just take Grover's algorithm and put it into phase estimation, and now you get this magical algorithm that can count. And there you go. And it's a whole brand new algorithm broken up, from two different algorithms. So thank you for listening. If you're interested in my Qiskit tutorials, they're free, and I want everyone to use them, and you can find them. They're on archive. And there's a second round coming out, hopefully within a month or two, that'll have QAOA, VQE, Shores, and all the more advanced ones.